All right, we'll start off with a very brief prehistory. We'll go over the origin of calculus and specifically why it was developed, what motivated the development of this new mathematics that we call calculus. And it comes down to problem solving. Throughout history, mathematics has been developed to solve problems. And one of the earliest examples just might be something really, really basic like counting. You might need to be able to count. You might need to count the number of sheep that you have or the number of cattle that you have. Or really counting anything is obviously useful. And counting was often done in very early times before number systems were developed. Counting was done with little stones. You might have a pocket full of little stones, and the number of stones in your pocket might correspond to the number of sheep you have in this field. And if you want to make sure that none of your sheep have wandered off or have been attacked or eaten or something like that, you could compare the number of stones you have to the number of sheep you have. And in fact, the word calculus comes from the Latin word for pebble. So the very origin, the very name calculus goes all the way back to this very, very early problem that was solved, the counting problem solved with using stones for counting. Geometry also, is very useful for solving problems. Being able to calculate things like perimeters and areas. These things were useful, for example, for land measurement. If you wanted to buy or sell a piece of property, it would help to know the area. Or also useful for agricultural reasons or tax purposes, being able to know the area around a field, for example. Also calculations of volume. Obviously, numerous practical applications to the theorems that we learn in geometry. Trigonometry was originally developed to solve certain problems in astronomy and also is very useful in navigation. But as things developed through the 17th century, there were tremendous advances in science and engineering. And there were new problems in physics and astronomy that the existing mathematics could not solve. And some new mathematics was needed to solve these problems. And I'll give you some examples. Suppose you have an object falling under the influence of gravity. So this little girl, for example, has climbed up this building and has dropped this piano off. So the piano is falling. Now we have equations that we know from physics that describe the motion of an object falling under the influence of gravity. We know the position is equal to the initial position plus the initial velocity times time plus 1/2 at squared, where a is the acceleration, and in this case the acceleration due to gravity, and t there is the time since it was released. We also can find the velocity. V is equal to v0 plus at. And these are fairly simple problems. Let's just take note of that. These are simple problems that can be solved if g is constant, or if a, the acceleration, is constant. But it turns out that the acceleration is not constant. Gravity is actually a little bit stronger down here closer to the Earth. As you go up higher and you're farther away from the Earth, gravity is a little bit weaker. Now, if you're going a height like from the bottom of to the top of a building, that kind of height, you're not changing your distance relative to the center of the Earth by an appreciable amount. So gravity isn't noticeably weaker at the top of a building than it is down at ground level. But in the 1600s, people were exploring ideas in astronomy. So picture this. Here's the sun, and imagine a planet orbiting the sun. And the planets don't move around the sun in circles. They move around the sun in elliptical orbits. And let's draw this a little bit exaggerated here, more like the orbit of a comet. The planet is way out here, far away from the sun at one part of its orbit, and then much closer to the sun at the other part of the orbit. Or in particular, something like a comet might have a highly elliptical orbit. And so as it comes in toward the sun, it's essentially falling toward the sun and picking up speed. And it's moving through this change in distance. All through its orbit, the distance from the sun is changing. So the force is changing. That is the force due to gravity, because the distance is changing. So the acceleration varies. So let's just take a few notes here. In a planetary orbit, the acceleration varies because the distance varies. So you can see that an equation like this would become obsolete as soon as it's used. You're trying to calculate the distance. Well, it falls a certain distance under a certain acceleration. But as soon as it moves any distance downward, that value for the acceleration changes because the distance has changed. And again, that doesn't make much difference with an object falling in our everyday experience, but over a large distance, such as we have with the planetary orbit, it does make a difference. And you can't do this. You can't solve this problem with these simple equations that deal with the constant acceleration. You need calculus. Another example is what I call the sliding chain problem. Let's draw a picture like this. Just draw like the edge of a countertop or something. And let's imagine this chain up here. So we'll draw these links hooked together. And the chain's hanging over the edge. And let's imagine it's slippery so it can slide off. So part of the chain is lying flat on top of the counter and part is hanging over the edge. So there's a certain length of chain on top of the counter and a certain length of chain hanging over the edge. And let's name those. Let's call this L1 and we'll call this L2 for length 1 and length 2. Now the downward force, there's this downward force pulling, and that downward force is the weight of the chain, but specifically the weight of the chain that's hanging over the edge, the part that we're calling length 2. Length 1 is supported by the countertop, so the downward force depends on length 2. The downward force depends on L2. Now we know Newton's second law will tell us how this accelerates. Newton's second law deals with forces and masses and acceleration, and specifically it says force is equal to mass times acceleration. So we can find the acceleration. Just solve for A, and that's simple. A is F over m, force divided by mass. So we can figure out how much this section of the chain weighs, divide that by the mass, and calculate the acceleration. Now the problem here is as soon as it moves, length 2 changes. As soon as it slides just one link, the amount of mass that's hanging over the side is bigger, so the downward force is greater. So this calculation immediately becomes obsolete because F changes as it moves. So I'll take a note of this. As soon as it moves, the force changes. As soon as it moves, F changes. So the acceleration, A, also changes. So we can't just solve this problem using this equation for acceleration because the A is constantly changing, just because the force is constantly changing. To really solve this problem correctly, we need calculus.